Hello, in this video we will look at the variational formulation of linear elasticity. This will turn out to be very useful later on. To begin with, consider a body which occupies a region of three-dimensional space. We'll call the body B, and suppose that there are surface tractions T and a body force B acting on the body. We will also assume that the body is fixed at certain part of its boundary, and we will call that boundary as, say, gamma d, and then the boundary where the force is applied will be called gamma n. So these two together exhaust the total boundary of the body, partial B. Now our primary field variable will be the displacement at each point x, that is how much a point moves as a consequence of the forces acting on the body. The displacement field will be a function of the form u from B to R3, which takes a point x to the vector ux, which has components u1, u2 and u3. So we will just use the standard Cartesian coordinate representation for our purposes. What is really important in the case of elasticity is understanding how gradients of the displacement work. So the gradient of displacement is just a function which takes a point x to a matrix gradient of u, which is composed of all the partial derivatives of u with respect to x. In a more proper treatment in the context of continuum mechanics, you will see that gradient of u is in fact what is called a second order tensor. But again, for our purposes, it is sufficient to think of it as a 3x3 matrix. Once we have the displacement gradient, we can define what is called the linear elastic strain tensor. This contains all the information about deformation of the body, and it's again a function that takes a point in the body to a 3x3 matrix, which is simply obtained as 1/2 the gradient of u plus the gradient of u transpose. You can also write this in terms of Cartesian components as epsilon ij equals 1/2 partial ui with respect to j plus partial uj with respect to I. Now, I have mentioned epsilon here as a function of x, which is a point in the body, but we will also later on consider a function epsilon as a function of the displacement field u. Now these are equivalent definitions, and depending on the context we may use the same symbol for both of these different functions. The identity, of course, is that epsilon as a function of x is nothing but epsilon as a function of u when u is evaluated at x. But we will use the same notation to keep things simple. The other important quantity is the linear elastic stress, which is denoted by sigma, which again takes a point in the body and gives you a 3x3 matrix. Now the linear elastic stress is a measure of the internal forces inside the body. Okay, and you might have studied this in basic linear elasticity courses. Suppose you take a point x inside the body and you have a small area A with normal n. The force acting on that small area is given by sigma times n, or you can also write this in component form as shown here. Now once you have the linear elastic stress and the strain, notice that these are symmetric matrices. Okay, the symmetry of the strain follows from simple manipulation of the indices, whereas the symmetry of stress is a consequence of the conservation of angular momentum. Now we will now come to an important aspect of linear elasticity, which is the linear elastic constitutive relation. So notice that the stress sigma and the strain epsilon both are 3x3 matrices, or they are second order tensors more precisely, and hence the quantity c that relates them in a linear fashion is a fourth order tensor, and this is the tensor of linear elastic constants. This tensor has a number of important properties, but for the moment it's sufficient to note just a few properties. And before I do that, let me just show you the component version of the equation that you just saw. And in this particular video, I will assume the Einstein summation convention, which means that repeated indices are summed up. As I said earlier, there are a few important symmetries of the linear elasticity tensor that you should know. The first is what is called as a major symmetry, which says that if you interchange the first two set of indices with the second two, the value of the tensor remains unchanged. There are also a set of what are called minor symmetries. These are obtained by interchanging either the first two indices or the second two indices. Okay, so you can either interchange ij to ji or kl to lk, and you will end up with the same value of the elasticity tensor. Now when you put this together, you will notice that instead of 81, you just have 21 independent components of the tensor C. Now this symmetry can be exploited to have the following identity, which is that the inner product of C and epsilon is the same as the inner product of C and gradient of U, and likewise for the quadratic form. So I urge you to verify this. The key quantity for us is the strain energy, or the linear elastic strain energy, which is given by 1/2 epsilon times C times epsilon, or using the identity given earlier, you can also express it in terms of the gradient of U, which is also shown in component form here. Now the principle of minimum potential energy, which will be our key result in this particular video, tells us that if you look at this particular functional E of U, which is W minus the work done by the body and surface forces. So this term is the work done by the body force, this is the work done by the surface tractions, and the first term is the energy stored in the body as a consequence of elastic deformations. Now the principle of minimum potential energy states that the equilibrium of the body is obtained by setting the variation of this energy functional to 0. Okay, and let's define this quantity delta E of U with respect to eta. Okay, eta is an admissible variation, which means that it has all the regularity properties of the displacement field, plus it satisfies the essential boundary condition, which means that on the Dirichlet boundary it takes a value 0. How do we define this variation delta E? That is defined as the directional derivative of E along the direction at U along the direction eta, given by this particular form. Here alpha is just a real number. Now there is a very simple way to evaluate this. All you have to do is to substitute the quantity U with U plus alpha eta in the expression for E of U, and then take the derivative with respect to alpha. Notice that alpha is a real variable, and hence you just have to apply the chain rule of differentiation to get the desired result. Now if you substitute, the integral has to be b dv. Please make the correction. So the integral involving the body forces is easily evaluated as follows, and using the same idea you can evaluate the integral involving the surface tractions, which again gives you an integral of t dot eta over the surface area, over the Neumann boundary. The important part, the slightly non-trivial rather part of the derivation is the derivative of the strain energy, but that is easily evaluated once you know the expression for it in terms of the gradient of U. So let's first substitute the U with U plus alpha eta, and then a simple calculation shows that it's a sum of two terms as shown here. And now we can exploit the symmetry of the linear elastic stress tensor constants to show that these two integrals are in fact identical. And once you do that, you have this compact expression for the strain energy. Now what you can do now is to use the divergence theorem to write this as a surface integral over the boundary of B of eta times C dot gradient of U times n, where n is the body normal, minus the divergence of C dot delta U times eta. Okay, so just to clarify, if you have a body B, then at any point on the boundary of B you can have the outward normal n, and that is what you see in the first expression here. So the n that you see here is the outward normal at the boundary of the body. Please do not confuse it with eta, even though they look similar. Now you can use the identity that the boundary is a union of the Dirichlet and Neumann boundaries to write this expression as the sum of two terms, And while I'm on it, I'll also use the fact that C dot delta U is sigma, the stress tensor. So you see that the boundary term splits into two terms, which is the sum of the the integrals over the Neumann and Dirichlet boundaries, and the term involving the Dirichlet boundary goes to 0 because eta vanishes there. So you just have this expression of eta dot sigma dot n evaluated over the Neumann boundary minus the divergence of sigma dotted with n, dotted with eta. Sorry, you have to be careful about that. Now once you do that, you can substitute this in the expression for the directional derivative of E at u along the direction eta, and this gives you this nice expression eta dot sigma dot n evaluated over the boundary minus the divergence of sigma dotted with eta. Okay, be careful, what you have there is eta not n, and this is the expression that you have. Now let's set the variation of E with respect to u along the direction eta to 0. Okay, before that, when you include the body and surface contributions, you see that you can rewrite them in this nice compact form. Okay, you have a surface term involving T minus sigma dot n dotted with eta minus the divergence of sigma plus b dotted with eta, but that's a volume integral. Okay, so this is the final expression for the variation of E. Now remember that the principle of minimum potential energy requires us to set the variation to 0. Okay. Now this implies two things. The first, both the integrands turn out to be separately 0. So you have the divergence of sigma plus b equals 0 in B, and the T equals sigma dot n on the Neumann boundary. Now this follows from a very important result called the fundamental lemma of the calculus of variations. This should be evident from any elementary course in the calculus of variations. I will give you a proof of this in the lecture notes. So what we have shown now is the following. If we set the variation of the energy functional with respect to u to 0 for any admissible test function eta, that is entirely equivalent to the governing equations of elasticity that you might have seen in the context of a solid mechanics course or a continuum mechanics course. Okay, so that you just have this simple elliptic partial differential equation, which is the well-known Cauchy-Navier equations of linear elasticity. We thus see that to solve the governing equations of elasticity, you can equivalently minimize the potential energy E defined here. Okay, so this will be a very important result here, and it's called the variational formulation of elasticity, and it simply tells us that we can solve a variational problem to understand the elastic behavior of solids. I'll stop this video here.